Right, students, let's consider Einstein coefficients. So radiative equilibrium means that all processes are in detailed balance: emission and absorption, excitation, de-excitation, ionization, and recombination. That means that no change in the quantities occurs. In that situation, we can consider Kirchhoff's first law that says that the source function is equal to the Planck function. But if you recall the definition of the source function, which is J over kappa, then this law reveals a connection between emission and absorption. So the emissivity J is equal to the Planck function times the opacity kappa. This form of Kirchhoff's first law implies that there is some relationship between emission and absorption at the microscopic level, which is understood because emission and absorption happen at the same frequencies. But this relationship between emission and absorption was unveiled by Einstein via a very elegant consideration. Consider that you have two discrete energy levels, the level 1 and the level 2, the lower energy and the higher energy. So imagine this. Imagine that there is an atom that has only these two states. There's the state 1 and the state 2. So the only processes that can happen are absorption. So the electron passes from the energy 1, absorbs a photon, gets to the state 2. And emission, when passed from the state 2 to the state 1 and then emits the photon. If you are in equilibrium, we must have the same number of emissions and absorptions. So let's derive here what the intensity in equilibrium is going to be if we are in equilibrium between emission and radiative excitation. So in equilibrium, we must have the same number of emissions and absorptions. So let's write this down. The number of emission events is identical to the number of absorption events. Now the number of radiative excitations, the number of absorptions, depend on the number of atoms that are in the n equal 1. So let's call this number n1. And depends also on the intensity of the radiation field, right? Now how many photons. Essentially, it's depending on how many electrons you have on the n equal 1 level and how many photons you have in the intensity field. And the number of emissions is proportional to the number of atoms that are at the n equal 2 level. And just that, right? It's going to emit a photon. Transform this into equalities. You call this proportionality coefficients the probability of these events. So the probability of emission events, call it A. A is the probability that an electron is going to transition back to the fundamental. And B is the probability of a radiative excitation event and absorption. Right, so let's put this in equilibrium. Now note that in local thermodynamical equilibrium, the population of a level Ni is given by the Boltzmann relation, where G is the multiplicity of the level and E is the energy of the level. Now, if the states N1 and N2 are separated by the energy of a photon, then you can write that N2 over N1 is given by G2 over G1. The energy of E2 is the energy of E1 plus the energy of the photon, which then becomes G2 over G1, e to the minus h nu over kT. So we substitute this expression for N1 over N2 into the expression for the intensity, and you find, so this is a function of the frequency. Now compare this radiation field with the Planckian. If this is a situation that you are in thermodynamical equilibrium, the intensity must equal the Planckian. But what is the Planckian? The Planckian is, so if you compare these two equations, this one for the intensity and this one for the Planckian, there is no way that they are identical. You can write this here in terms of 1 over the exponential, but you are missing the minus 1 in the denominator. The mathematical form of the two equations is different. So there is no way that this model can be complete. The minus 1 in the denominator means that there is a term missing in this equation. There is some radiative process that we're not considering.